Hello. In this video, we're going to be taking a look at the notes for AP Physics 2, electric potential and electric potential energy. Please remember to pause or rewind the video as needed. Let's begin. Section 14.5, electrical potential energy. Two charges, big Q and little q, are separated by distance r. The potential energy of the system is... Well, let's take a look at that concept and let's derive the potential energy. You see, potential energy, if you remember, was the potential for some force to do work, meaning they're related. So now work is equal to force times distance. I'm going to call distance r. And the force applied between two charges, so if you have two charges, Q and Q, let's say big Q and little q, then there's a force of either attraction or repulsion between them based upon the sign of the charges. So in place of force, we would have K, Q, big Q, little q, over R squared times R. And that leaves you with K, QQ over R. And so that's how we can derive the equation for electrical potential energy. So the book refers to it as U sub Q. However, most publications, including on the AP exam itself and the formula sheet, is going to refer to it as U sub E, which is electrical potential energy. So U sub E is electrical potential energy, which, remember, potential energy means the potential for some force to do work. So now we're talking about the potential for an electric field to do work on a charge. That's what electric potential energy is all about. Okay, so the equation would be K times Q1 times Q2. Well, actually, since we're using big Q and little q, we'll say K big Q times little q divided by R. Now, one thing to note about this, there are no absolute value bars like you saw in some of the previous things. So in the electric force, it was K times big Q little q over R squared. And we put absolute value bars there because the force, the sign of the force, was either positive or negative depending on the direction of the force was positive or negative depending on the sign of the charges, repulsion or attractive forces, right? But energy does not have a direction. You either gain energy, lose it. You increase it or you decrease it, right? So with that said, you can put negative charges in here where you did not put them here. So that is a fundamental difference. The vector quantities of force and field, we put absolute value bars. The scalar quantities of potential and potential energy, we're starting with potential energy, you can put negatives. So you can put negative charges in for Q. Okay, so you can put negative signs in there. Again, something to consider that if we, as we look at this, the potential energy between charges is inversely proportional to the distance between the charges. So at as the distance gets really small, right, then the potential energy is basically infinitely high, and then vice versa. If an object is, let's say, infinitely far away, then that means the potential energy essentially goes to zero. That's going to be an important designation that we're going to use. That's going to be an important connection that we're going to use when we start looking at applying conservation of energy. Okay, so what happens if the charges are unlike, they have unlike signs, so opposite signs like this and this, then the potential energy is negative. Okay, why is that? Because remember, you can put a negative sign in for Q, and thus you end up with a negative potential energy, right? If the charges are the same, with negative negative or positive positive, then you're going to end up with a positive energy. Let's take a look at the next example. All 16 charges shown below have equal magnitudes but different signs. For each charge, draw a bar graph representing the electric potential energy of the two-charge system. Okay, so again, remember, electric potential energy is inversely related to the distance between the charges, and also that unlike charges are negative potential energy, like charges are positive potential energy. So that's going to influence how we draw the bar graph. All right, let's do this. Now, I see for example A, let me zoom in here. For example A, I see that they're opposite charges, so we should have negative potential energy, and they're very far apart. So that means we're going to have a small negative potential energy drawn for bar graph A. Bar graph B, you have positive charges. No, I should say not positive, but positive and positive. So you have like charges, which means you're going to have positive potential energy. And since the distance is very close together, you're going to have a much larger positive potential energy. So we're going to draw the bar graph like this. In letter C, you have negative. So A was negative, B was positive. C is going to be negative because they're unlike signs, but they're very close together, so it's going to be a large negative. I'm going to draw it like this. We have opposite signs here, so we're looking at negative potential energy, but they're really far apart, so we're looking at very small negative potential energy. In diagram E, we have like charges, so that's positive potential energy. Since they're so far apart, that would be very small positive potential energy. Here we have like charges, that's going to be positive. They're again very far apart, so again we have very small positive potential energy. Like charges, positive potential energy, very close together. Therefore, we're looking at much larger positive potential energy. And finally, in letter H, we have opposite charges. Therefore, you have negative potential energy. And since they're so close together, you have large negative potential energy. Okay, so to summarize, we have small negative potential energy for letter A, large positive potential energy for letter B, large negative potential energy for letter C, small negative potential energy for letter D, small positive potential energy for letter E and letter F, large positive potential energy for letter G, and large negative potential energy for letter H. So for the bottom, let us summarize. It says situation wishes it could be situation. Now, what it's basically saying is, for instance, for example, let's take situation B. Situation B has two positive charges that are really close together, and they don't want to be close together because positive and positive repel each other. We know that. So situation B wishes, change my lettering there, wishes it could be situation E because you have positive charges that are just farther apart, essentially. And they don't want to be close together because they repel each other, right? But if this happened, if B became E, then the charges get farther apart and you can see the potential energy decreases. Another example of this would be, let's see, letter G. So if we take a look at letter G has two negative charges, and letter G wishes it could be letter F. Why? Because those two negative charges in letter G don't want to stay next to each other. They want to repel and push each other farther away, and that would be the result of letter F. And of course, if it would do that, if G became F, again, you can see there's a decrease in potential energy. Now, let's take a look at A. Now you're looking at opposite charges. Opposite charges want to attract each other, right? So if A, for instance, became H, A wants to become H because attractive charges want to, opposite charges, want to attract each other, and they'll be more attractive the closer they are. So when they're really far apart, that's a weaker force. So they would prefer to be closer together, so it's stronger attraction. So A wishes it could be H, and if A became H, the potential energy, you can see, increases, right, from small negative to large negative. And then finally, if D, which is really far apart, kind of the same thing, really, D and C, right, are really the same thing as A and H, same concept. And if D became C, you can see there would also be a potential energy increase. The reason that charges attract and repel each other the way they do is because they want to do work. You see, recall, work is an applied force over a displacement. And if applied force is going the same way we do work, then that's a positive increase in energy, meaning that's positive work done. If we have a force that's going against the object's displacement, that is a negative change in energy, and therefore negative work was done. Suppose you have 3 charges in your system. How would you find the potential energy of that system? Very easily. So let's say you have the potential energy. So you find the potential energy of each pair of charges. So let's say you have 3 charges. I'm going to call them charge 1, charge 2, and charge 3. You would basically find the potential energy of all 3 combinations. You would find the potential energy between 1 and 2. So that would be K, Q1, Q2 over R. Then you would find the potential energy between 2, 3. That's K, Q2, Q3 over R. Now it's R1, 2, the distance between R and 1, 2, and the distance between R, 2, and 3. And then finally, you would find the potential energy between 1 and 3, which would be K, Q1, Q3 over R1, 3. And then you would simply add these up. Right? We would add these potential energies to find the total potential energy. The convenient part about dealing with a potential energy in terms of, instead of, let's say, a vector quantity like force or field, is we don't have to worry about vector components. We simply find the energy, whether it increased or decreased, and we simply add it if we're talking about the summation of a bunch of different energies. Let's take a look at this example. 3 charges are brought together from infinity and placed in the right triangle as shown. Q1 has a mass of 2 kilograms and has a charge of 20 microcoulombs. Charge 2 has a charge of 10 microcoulombs, and charge 3 has a charge of negative 10 microcoulombs. Not micro, I'm sorry, millicoulombs. Do remember that millicoulombs would need to be changed to times 10 to the negative 3 coulombs when you're doing the actual work. So what's the potential energy of the 2-3 system? So we're focusing on just those two. We would go U23 is equal to K Q2 Q3 over the distance between them. So this would be 9 times 10 to the 9 times charge 2, which is 10, times 10 to the negative 3, times Q3, which was negative 10. Kind of running out of room here. Times 10 to the negative 3. All over the distance between them. The distance between them would be the 3 meters. Remember not to square this. This is not force. This is energy. Throw that in your calculator. Okay, you should have been able to get about negative 300,000 joules. What is the potential energy of the 1, 2, 3 system? Well, to do that, we got to find the potential energy of 1, 3 and the potential energy between 1 and 2. And then we have to add all of them up. So 1, 3 would be K Q1 Q3 over R. So it's 9 times 10 to the 9 times Q1, which is 20 times 10 to the negative 3 times Q2, which is 10 times 10 to the negative 3. All that is divided by the 4-meter distance between them. And you get a, let's see, I'm sorry, not divided by that, divided by 5 meters. My apologies, it's this right here. And 1, 3 would be, charge 3 would be the negative 10. There we go. So that comes out to about negative 360,000 joules. And then for 1, 2, that's the one I was currently doing right now. K Q1 Q2 over R, that one's going to be 9 times 10 to the 9. And Q1 is the 20 times 10 to the negative 3 times Q2, which is 10 times 10 to the negative 3, all divided by 4 this time, and we end up with about 450,000 joules. The potential energy for the system would just simply be the sum of all 3. It would be the negative 300,000 plus the negative 360,000 plus the 450,000. And we get about negative 210,000 joules.
Suppose a person assembled these charges by bringing them in from far away and fixing them in place with bolts. How much work did the person do to assemble these charges? Was the system happy to be assembled or difficult to assemble? Explain your answers in a paragraph. first let's start with the solution for the potential energy of the system being negative 210 joules. Let's make some sense of that answer. First, let's explore the following. If two charges have like signs, then potential energy represents the work done to bring them together from an infinite distance. This is because like signs do not want to be together, they want to be apart. If two charges are unlike, they want to be apart, they want to be together. So two charges with unlike signs, the potential energy represents the work done to separate them in infinite distance. Since the electric potential energy was negative, they want to be together, just like opposite signs would be. This means they are happy to be assembled. If the bolt is taken out of Q1 so it can be moved around, will the charge leave and go very far away? Explain how you know. Let's go back to the question again. So what we're referring to is this charge right here. If that charge is unbolted, what is it basically going to do? Well, to answer that, we need to find the potential energy on that particular charge. And then from the potential energy, we'll be able to see whether or not it is happy to be there or does not want to be there. If it's happy to be there, it's going to stay put. If it does not want to be there, it will accelerate far away. Well, first, we can take a look at the potential energy calculation here. The potential energy on object 1 is the potential energy involving charge 1 and 3, and then charge 1 and 2. These ones here. Once you find the potential energy involving those charges individually, then you add them together. And we get a potential energy, the potential energy of that charge Q1 is 90,000, positive 90,000 joules. What this means is it has positive potential energy. It wants to go to zero potential energy. Everything in the universe wants to go to zero potential energy. So what it will do, since it is positive, it wants to essentially be much like, I'm going to draw the analogy that we did earlier. It wants to be like two charges that are like sign, and what do they want to do? They want to repel. They don't want to be together. And so naturally, what is the Q1 going to do? It is going to fly off very far away. And when it has reached an infinite distance, that potential energy will become kinetic energy. Find the speed Q1 when it reaches very far away. Well, we know that the potential energy, rewrite this, there we go. The potential energy of 1 becomes the kinetic energy at an infinite distance away. Okay, so what that means for us is that the kinetic energy will also be 90,000 joules. So the kinetic energy equals 1/2 mv squared, and solve for v. Multiply by 2, divide by mass, square root. That's 2 times the 90,000 divided by, now the mass was told in the problem as a 2 kilogram mass. Well, that conveniently cancels, and, well, the square root of 90,000 is exactly 300. So it'll be moving and traveling at about 300 meters per second at an infinite distance away. This is a really good example of when conservation of energy becomes applied in electrostatics. Section 14.7, charge separation and photocopying, putting it all together. Example, the charge placed on a Van de Graaff generator is about 5 times 10 to the negative 6 coulombs. The ball of the generator has a radius of 16 centimeters, or 0.16 meters. Suppose that a proton is placed on the surface of the Van de Graaff's ball and released from rest. How fast would the proton move when it reaches a far point away? First, let's take a look at what a Van de Graaff generator is.
Hi gang, one thing I get asked for is to do some Van de Graaff generator demonstrations, and to explain how they work too. So here's the inside scoop. The thing that all these demonstrations have in common is that they interact with the top dome. So let's see what's going on there first. The top dome of a Van de Graaff generator is either positively charged or negatively charged. That means it either has more protons and electrons, making it positively charged, or more electrons and protons, making it negatively charged. The key point is that it's kept that way. If we add some electrons to a positive dome, by arcing to it for example, that makes it less positive. But those electrons are quickly pulled away from the dome, and the dome is back to being positive again. The same is true if we were taking electrons from a negative dome. New electrons are quickly put back on it to make it negative again. There's an endless supply of charge, and it's constantly being replenished. Now on with the demonstrations. I'll start with this well-known hair-raising demonstration. Now my hair isn't long enough for it, so I'm going to put on this collection or crown of strings on my head instead. Start with the Van de Graaff generator turned off and not charged up. That's so that you don't get a shock when you first touch it. Next, stand on an electrically insulating platform. I'm wearing rubber-soled sneakers with the laces tucked away so they don't touch the ground. That's good enough. Next, put your hand on the dome. Then turn on the Van de Graaff generator. Your hair should now raise up. Give your head a shake to help separate the strands of hair. When done, you can remove your hand, as long as you're still insulated from the ground. I discharged myself by touching a wire connected to the ground, getting a small shock. I then turned the Van de Graaff generator off, still keeping myself away from it in case of a shock. Then I bring the end of the ground wire near the dome and touch it. It's now safe. So how does this work? Your skin is not a great electrical conductor, but it does conduct some electricity. Since you're touching the dome, you're basically a part of it. If the dome is positively charged, then you become positively charged. Electrons are taken away from you and your hair by the Van de Graaff generator. That means your hair now has more protons than electrons. It's positively charged. The important principle that makes your hair rise is that like charges repel each other. So each positively charged strand of hair repels each other positively charged strand of hair. They try to repel as far away from each other as they can. But a clump of hair stuck together can act as one. Shaking your hair separates the strands so that they can act individually and repel each other. In this demonstration, a stack of metal pie plates fly off one by one. How does that work? Well, the outer surface of the stack becomes charged, not all parts of the plates at once. That's all the visible surface of the top plate and the visible edges of all the other plates. That's due to the Faraday cage or Faraday ice pail effect. Notice that just as with the hair, the plates are charged the same as the dome, positive in this case. Only the top plate is free to move, since it's on top, and the edges of the top plate and the plate below it repel each other. Remember, like charges repel. As the first one rises, the newly exposed surface of the second one becomes charged too, and repels the top plate more strongly. The top plate is repelled away. Anyway, now we have a new top plate and the whole process repeats. This demonstration consists of my crown of strings in direct contact with the top of the Van de Graaff. When the Van de Graaff is turned on, the strings rise and separate, just as your hair did, for the very same reasons. Here a bunch of strands of toilet paper are taped to the dome instead. You don't need a big Van de Graaff generator to do demonstrations like this. Here's a small homemade one. These cans have paint on them. Since this Van de Graaff is weak, it's best if you first sand off the paint wherever your demonstration objects will touch it. Here grains of rice become charged and are repelled off. That's because they become charged with the same charge as the can and as each other. And once again, since like charges repel, they repel from the can and each other. And here strips of toilet paper rise up. And in this one, I'm making my homemade Van de Graaff generator run my homemade Franklin's Bell. But I have separate videos all about Franklin's Bell, so I won't say more here.
So to find how fast the proton would be moving when it reaches a point very far away, we're essentially going to be using conservation of energy to solve this problem. We know this because we start with electrical potential energy on the surface of the Van de Graaff. And as the proton is racing away from the Van de Graaff generator, it's losing potential energy. And as it reaches an infinite distance away, as the distance r approaches infinity, the electric potential energy approaches zero, which means the electric potential energy has converted completely into kinetic energy. So we can use the kinetic energy to find how fast we're going. So the kinetic energy at some infinite distance away, we'll call that kinetic energy final, is equal to the initial potential energy, which is electric potential energy, and that's going to be K times Q times, I'll call it big Q, over R, the distance away. Now, little q is going to be the charge of a proton, which is 1.6 times 10 to the negative 19 coulombs. The big Q, well, that's the charge that's placed on the Van de Graaff. Now, the charge on the surface, we use the distance. We actually use the radius of the Van de Graaff, and here's why. If we were to look at the radius of the Van de Graaff generator, the ball itself, the surface of the Van de Graaff generator has become positively charged, and the potential is exactly the same all the way throughout. So if we were to actually look at a graph of potential, okay, that's the voltage. It's the amount of work done on an individual charge. And we were to look at that, let's say R naught represents the radius of the sphere, and this is voltage versus distance. The actual potential would be constant within the radius, because all conductors themselves essentially are what are called equipotentials, meaning there's no change in potential. And why is there no change in potential? Because a conductor itself, electrons are just going to move freely all the way through the conductor with no work required to move them. So if no work is required to move them, that means there's no change in energy. That means there's also no change in potential. There's no difference in potential. Therefore, it's constant potential within a conductor. Now, once you leave the surface of the conductor, the potential is going to decrease to zero as we get infinitely far away. Some other data points to keep in mind for solving this problem: the mass of the proton is 1.67 times 10 to the negative 27 kilograms. We get this from our table of information, okay? And K, charge constant K, is 9 times 10 to the 9. Okay, so the first thing we want to do is we want to figure out the potential energy, because the potential energy on the surface of the Van de Graaff is going to be the same as the kinetic energy infinitely far away due to conservation of energy, right? So let's figure this out. We're going to go 9 times 10 to the 9 times the charge of the proton, 1.6 times 10 to the negative 19, times the charge of the Van de Graaff, 5 times 10 to the negative 6, and all of that is over that radial distance of 0.6 meters. Take a second to plug that in your calculator. Should be getting something in the neighborhood of about 4.5 times 10 to the negative 14 joules. Now, if the kinetic energy infinitely far away equals this potential energy on the surface of the Van de Graaff, that means that this value right here also is set equal to 1/2 mv squared. And we will solve for v. So v is equal to the square root of 2 times the kinetic energy divided by the mass. So it's 2 times 4.5 times 10 to the negative 14 joules divided by a very small mass of 1.67 times 10 to the negative 27 kilograms. Take a second to plug that in your calculator. And you should be getting somewhere in the neighborhood of about 7.34 times 10 to the 6 meters per second. Sketch conceptual diagrams of the proton's speed and acceleration as functions of time, assuming the proton is released from rest at time equals 0. In the acceleration next to each graph, explain why. Well, the speed essentially starts at 0 because the kinetic energy starts at 0. We start with nothing but potential energy. We start with 0 kinetic energy, therefore we start with 0 speed. And the speed is going to be increasing at a constant rate. We're going to be accelerating. Initially, we're going to be accelerating as the object is flying away. But as we get infinitely far away, we're going to be reaching a point where the potential energy goes to 0. And where the potential energy goes to 0, no work is done. And no work is done to change the energy of the proton. So therefore, you're going to kind of end up with a constant velocity. So the kinetic energy that you reach is corresponding to a velocity that we calculated here that remains constant the rest of the way. Seemingly, the acceleration we experience initially is going to drop off to 0 as we approach that infinite distance away. Section 15.3, the V field. Well, V stands for voltage, but it also stands for electric potential. Let's define it and let's explain a little bit more clearly. Electric field is an effect in space that causes a charged object to feel a force. Electric potential is the work needed to move a unit of charge from a reference point to a specific point in an electric field. The symbol for potential is V, just like we wrote here, and the units for potential are the volt, because it's essentially voltage. So you could write out the word volt, or you could use capital letter V. Now this is the one time all year where the variable and the unit are the exact same letter, capital V. The basic equation for electric potential is the work needed to move a charge. So it's work divided by charge. Or we could write it as the potential energy per unit charge. Explain what a 9-volt battery does as electric charge passes through the battery. Well, each coulomb of charge will gain 9 joules of electric potential energy as they move from the negative to the positive terminal of the battery. Let's take a look at an example. In a television tube, electrons of mass 9.11 times 10 to the negative 31 kilograms and charge 1.6 times 10 to the negative 19 coulombs are accelerated through a potential difference of 3,000 volts. If they are initially at rest, how fast do they pass after through this potential difference? So this is essentially going to be conservation of energy again. So initially, if they're at rest, the initial energy would be electric potential energy. And this, the final energy, would be kinetic energy. And this basically converts into that. Electric potential energy, if we use the equation up here, is going to be Q, the charge times the potential, times the voltage. And kinetic energy is equal to 1/2 times the mass times the velocity squared. And since these are equal, these are now equal. We just set those two portion equations equal to each other. So charge times voltage equals 1/2 mass times velocity squared. And you're using that to figure out the speed. So to calculate the speed, to solve for this, we have to multiply by 2, divide by mass, and square root. And if we do that, the speed is the square root of 2 times Q times V, all divided by M. So that would be 2 times 1.6 times 10 to the negative 19 coulombs times the 3,000 volts, all divided by the mass of 9.11 times 10 to the negative 31 kilograms. Take a second to put that in your calculator. Should have ended up something in the neighborhood of about 3.25 times 10 to the 7 meters per second. What is the equation that gives electric potential created by charge Q located at a distance r away from the charge? Well, if electric potential is electric potential energy per unit charge, then remember electric potential energy was Q times charge divided by R. Well, let's substitute this right here in the top, and we get that voltage is equal to K times Q over R times the Q down there. And you can see one of those is going to cancel, leaving you with voltage is equal to KQ over R. Yes, charges can be negative in this calculation too. So just like electric potential energy, electric potential, you can put a negative charge in there to calculate. How do we calculate the electric potential at a point of interest if there's more than one charge? Well, the sum total of the potential is equal to the voltage on charge 1 plus the voltage on charge 2 plus however many charges there are. Very simple, we just add it up. Fill in the compare and contrast table for gravitational field, and electric potential. So let's start. The symbol for the gravitational field is lowercase g. You know it better as the acceleration due to gravity, but it also represents the strength of the gravitational field. Well, the symbol for the electric field is a capital E, and the symbol for the electric potential is a capital V. The units for gravitational field are meters per second squared or newtons per kilogram. The units for electric field could either be newtons per coulomb or volts per meter. Gravitational field acts on objects with mass. Electric fields act on objects with a charge. Electric potential, right, also acts on objects with the charge. Gravitational fields created with objects with mass. Electric fields are created by objects with charge, as are electric potential. A gravitational field gives an object a gravitational force. Electric fields give an object an electric force. Electric potential gives an object electric potential energy. The basic equation for gravitational that involves gravitational field is the gravitational force is equal to mass times the gravitational field. The electrical version of that would be the electrical force is equal to the charge times the electric field. So instead of mass, we have charge. Instead of gravitational field, we have electric field. And voltage is equal to the potential energy per unit charge. Gravitational field is a vector. Electric field is a vector. Electric potential is a scalar, meaning has direction, has a direction, has no direction. The basic equation for the strength of the electric field is G times M over R squared. For electric field, it's E equals KQ over R squared. And for potential, it's KQ over R. Section 15.4, relating V field and the V field. What is the relationship between electric potential and electric field? Describe it in words and equation. Okay, well, with an equation, an electric field can be represented as the potential difference, or the voltage, divided by the distance between. Now, if you solve this, this means the electric potential is the electric field times the distance between 2 points. Electric field and electric potential are perpendicular to each other. I'll save that until the next part of the lesson. Imagine a landscape made completely out of smooth concrete. The concrete is not flat, but instead formed into hills and valleys. On this smooth concrete are marbles that roll without losing energy to friction. The marbles have mass if they all feel a force directed downhill from where they are. The segment of the hills or valleys of landscapes are shown here on the left-hand side, and on the right-hand side, we have a contour map that corresponds to the 3D diagram that's shown to the left. In this analogy, the height of any point represents the value of the electric potential at that point. So you can think of this contour map is showing, all these lines here are showing essentially the altitude at any one point on the map. And they represent, as an analogy, the electric potential at that point. The slope at any point represents the strength of the electric field. You can kind of equate that to when if we look at the contour map here, when the contour lines are very, very close together, that's a steep slope that indicates a very, very tall hill. Or in this case, a strong electric field. The marble represents positive charges. Let's take a look at this next example. In order to create a spark through air, the electric field in the air must be 3 times 10 to the 6 newtons per coulomb. Suppose two objects are, let's just say for simplicity, 1 meter away from each other when a spark passes between them. What must the potential difference have been in order between them in order to create that spark? Well, the potential difference is equal to the field times the distance. So we simply take the field strength of 3 times 10 to the 6 newtons per coulomb. And in this case, I'm going to use the volts per meter unit for electric field. You'll see why in a second. Times 1 meter cancels, leaving you with a potential difference of 3 times 10 to the 6 volts. Let's build the following analogy. Consider a cart moving very slow down each of the different hills. So you can see hill 1, you go down 10 and over 10. So there's a slope of 1, slope of negative 1. For hill 2, you're going down 10 over 5. There's a slope of negative 2. In hill 3, you're going down 20 over 20. That's a slope of 1, negative 1. And in hill number 4, you're going down 20 over 10. That's a slope of negative 2. Now, if we consider the hill itself, we start with kinetic energy equals, the kinetic energy initial would be 0 because we start from rest. The potential energy initial is mgh. The kinetic energy is 1/2 mv squared at the bottom because the potential energy has now come to 0. And so what that means for us is the mgh at the top transforms into the 1/2 mv squared at the bottom. And if we solve for v, the masses cancel, multiply by 2, square root, we get that v is equal to the square root of 2 times g times h. What that basically means for us is that speed is dependent on the height. So, on which hill does the car have the greatest force? Well, the greatest force would be the ones that have the greatest acceleration. You're going to accelerate the greatest on the ones with the steepest slope. Therefore, 2 and 4. Which ones have the greatest speed in the bottom? Well, that would be 3 and 4 because speed is proportional to height. Real specifically, it's proportional to the square root of height because we can see that, again, speed is equal to the square root of 2gh. And 3 and 4 have a much greater hill. So similarly, the analogy is built over on the right-hand side with a proton. Proton is placed at rest on the positive plate in any of the sets of plates shown. And so in situation number 1, we have a potential difference of 10 volts separated by 10 centimeters. In picture 2, we have a potential difference of 10 volts, 10 minus 0 is 10 volts, separated by 5 centimeters. In picture 3, we have a potential difference of 20 volts separated by 20, and in picture 4, we have a potential difference of 20 separated by 10. In which one does the proton have the greatest force? Well, here it was the one with the greatest acceleration, which means the greatest gravitational field, the greatest G field, right? Well, this one is going to be the one with the greatest E field. The one that experiences the greatest electric field is going to experience the greatest force. Just like the one that experiences the greatest force is the one that has the greatest G field. Okay, so now what do we know with that? We know that the electric field is the potential difference divided by the distance. So I can calculate that for each one, just to kind of get a way to compare. The potential difference would be 10 volts over 0.1. I've got to change that from centimeters to meters. And we get 100 volts per meter for the first situation. For the second one, we're going 10 volts divided by 0.05 meters. That would be 200 volts per meter. In the third example, we're going to go 20 volt potential difference divided by 0.20 meters. That would be 100 volts per meter. And in the last example, the electric field would be 20 volts of potential difference between the plates divided by 0.10. That would be 200 volts per meter. So which ones have the greatest force are the ones with the greatest E field. Those would be 2 and 4. The ones with the greatest speed, well, in this case, potential energy still converts to kinetic energy, just like it did before. Here, it was gravitational potential energy converting to kinetic energy. Here, it's electrical potential energy converting. So electric potential energy is Q times V, and that's equal to 1/2 mv squared, solve for V, and it's 2 times Q times the voltage divided by the mass. Now, the mass stays constant, charge stays constant, so what we're really saying is the speed is proportional to the square root of the potential. The speed depends on the potential difference. So the ones with the greatest potential difference would be 3 and 4. What is an equipotential isoline? It is a line of equal potential or equal voltage. How are equipotential lines oriented with respect to electric field vectors? They are oriented perpendicular to these lines. What map features do we relate equipotential isolines to? Those would be lines of equal altitude on a map. So in this next example, we have 3-point charges that are creating the electric potential shown with all these isolines. We're going to draw arrows at each of the labeled points indicating the direction of the electric field. Now remember, electric fields are perpendicular to the isolines. So, and electric fields always go from positive voltage to negative voltage. They always point from positive to negative regions. So I'm going to be at point A, going away from the positive 80 region, and so I would draw a perpendicular arrow. It's perpendicular to the surface at that point. at B. It's going to be that point. And something to consider, remember, the slope of the line is indicative of the strength of the field at that point too. And so let me go back to A. The slope of the line is represented by kind of the distance between two adjacent lines. When they're really close together, that's a steep slope. So this, I think, would actually be drawn as a much longer electric field because it's much stronger when the iso lines are closer together. Here, the iso lines are much farther apart in B and C, so I'm going to draw a perpendicular E field for both of those, but shorter this time because like I said, the iso lines are spread farther apart. That means the electric field is a little weaker there, as is with D. But E, they're starting to get closer together again, so I would expect to draw this one a little bit longer. But notice all of them are perpendicular to their respective isoline. At which point is the electric field the strongest? Well, it's going to be the strongest, like we said, in the one where the lines are really close together. Steepest slope. Weakest, well, it's going to be the one that are really, really far apart. I would say that's either B or possibly D, really spread apart on both of those. More so than C. An object, a 5 kilogram object with a charge of 0.1 coulombs is released from rest at point A. It follows the path to point E. How fast is it moving when it reaches point E? Well, again, we're going to use conservation of energy to solve this. Okay, and conservation of energy tells us that the initial energy equals the final energy, total energy, and we're starting with if we're released from rest, that means we're starting with electric potential energy, and it's going to be converted into kinetic energy. Okay, but it's not just kinetic energy, it's kinetic energy and there's going to be some potential energy. So I'm going to call this the potential energy at point A. This is going to be the kinetic energy at point E and the potential energy at point E. All right, let's write these into their respective equations. The potential energy equation is charge times voltage, so Q times VA equals 1/2 mv squared plus Q times VB. Okay, and we're basically going to, let's go ahead and take this and subtract it over to the side, and we get Q times VA, QVA minus QVB, and that's Q times VA minus VB if you factor out the Q. And that's 1/2 mv squared, and so that's Q times the potential difference times 1/2 mv squared. To solve for V, you have to multiply by 2, divide by m and square root. So V is the square root of 2 times Q times the potential difference divided by the mass. So 2 times 0.1 charge times the potential difference. Now, what's the potential difference from A to E? Well, A is 70, E is negative 30. So the potential difference there is 70 minus a minus 30, or 100. Divide that by the 5 kilograms of mass. And we're looking at about 2 meters per second. The same object is now released from rest at point B, and it follows a path to point C. How fast is it moving when it reaches point C? Well, looking at the picture, point B and C are on the same iso line, which means they have the same potential. Therefore, if the potential is the potential energy for each charge. It means this charge has the same potential energy at B as it does at C. Since it has the same electric potential, because it's on the same iso line, it has the same potential energy. That means when it gets to C, it will have, and it's released from rest. So if it's released from rest, all you have is potential energy to start with, no kinetic energy. It means when you get to C, you have to momentarily stop because you can't have any kinetic energy at C either. The diagram, not to scale, shows 3 parallel plates set near a ruler. Assume the plates are longer than their separation distances. The middle plate is connected to a ground, and batteries and wires are connected as shown. Okay. Plot a graph of electric potential in the region between the plates as a function of the position on the ruler. Well, let me see. The electric potential, if we look at the battery here, this kind of tells us everything. The positive side of the battery, this is a battery symbol here. The uneven parallel lines are always such that the longer end is the positive side, the shorter end is the negative side. That means a battery has a potential difference of 12 volts on the positive side and 0 volts on the negative side. Which basically means this is going to be 12 volts, this is going to be 0 volts. And if you look at the spacing, the distance between them is 4 centimeters. So if we start at 12 volts, here on this particular bar, and what is the voltage when we get to this point? That voltage would be 0. So the first part of the graph is going to be looking like this. Okay, so now before we complete the rest of the graph, let's draw and label the electric potential lines in the 2 regions of the plates. Okay, so we're going to have lines of equal potential at various points along the way. Okay, and here's basically what it means. The electric field is going to be constant all the way through this thing. Okay, and what's going to happen is every centimeter, so what we have is the voltage is the field times the distance. Since the field is constant, the voltage is going to increase with distance. So for instance, if we go 1 centimeter away from 0 volts, you're going to be at, from 3. This is 1/4 of the way, 1/4 of the way, 1/2 of the way, 3/4 of the way, and then all the way to the other line. So half of the way would be 6 volts, quarter of the way would be 3 volts, 3/4 of the way would be 9 volts. And so we're looking at a 3-volt separation for every single centimeter. On the other side of the ruler, well, if you add up all these, this would be 0, 1.5 on this side, and then if you added them all up, 0 plus 1.5, you basically end up with 0 on one side, on this side right here, and then you end up with 1.5 plus 1.5 plus 1.5 plus 1.5, which is 6 volts on this side. So the separation, the voltage difference, the potential difference across this side of the region would be 6 volts as opposed to 12 volts over here. Now, if this is 0 on this side and this is 6 on this side, so that's going to be 6, that means the halfway point over here would have to be 3. And you can see it's spaced with 6 different centimeters. So that makes that 1 volt, 2 volts, 3 volts, 4 volts, 5 volts, and then 6 volts. So to complete the instructions and draw the ISO lines, it would basically look like this. I'm just going to draw dashed lines at each voltage because everything on this line is 6 volts. Everything on this line, right, has a potential of 3 volts. Everything on here is 0. Everything on this one is 1 volts. Everything on this one is 2, and so on. So I'm just going to draw the ISO lines or the equipotentials. There we go. Draw and label the electric fields between the two regions. Well, the electric field, we can actually calculate them just to kind of be on the same page. The electric field in the left region, the electric field would be a 12-volt potential difference divided by 0.04 centimeters. That comes out to be about 300 volts per meter. On the right-hand side, so this is electric field on the left side, the electric field on the right side is going to be 6 volts of potential difference divided by the difference between 4 and 10 would be 6 centimeters. So 0.06 meters. 6 divided by 0.06 is 100. Okay, so what it means to draw this, it means that we're basically going to draw electric field lines going from the positive to the negative. So it would look like those would be the E field lines, and I'm drawing them all the way across. Okay. Now, the lines for the other side should be 1/3 of the length going from positive on this side to negative this side, drawn to the left. But they should be about that long, if I'm drawing them proportionally to their magnitudes. It would be something to that effect. Now, the electric field does stretch across the whole gap. It's just I'm representing with shorter arrows to represent the fact that it's a weaker field. Now, to finish off the graph, you basically get to a potential of 6 volts when it's all said and done. So the graph may go from 12 to 0 like this, but then it goes from 0 to 6 volts like this. What is the electric field direction and magnitude in the left and right space? Let's go ahead and divide this in two. Left, right. Well, the electric field is essentially the slope. It's the negative of the potential difference over the distance, or the negative slope, which is going to be negative times the negative 300 volts per meter that we got for the electric field slope, or 300 volts per meter. Directed to the right, so it's positive. And then the E field here is going to be the the negative 6 volts over the negative 0.06 meters, or the negative 100 volts per meter. What that basically means, 100 volts per meter is the magnitude, but to the left. If a proton was released from rest at the 7 centimeter mark, and a proton is allowed to pass through the center of the plate, the hole in the center, where will the proton come to rest on the other side? Explain what's going on. Well, where is 7 centimeters in this whole thing? 7 centimeters is right here. And you can see there's a potential difference between 3 and 0 from the 7 centimeter mark. The proton is going to travel to a point of equal potential on the other side, meaning 3 centimeters. And here's an analogy you can kind of draw. If you had a bowl and you dropped a marble from a certain height on that bowl, it's going to roll all the way until it gets to the other side, so that the potential energy that it started with is fairly similar to the potential energy it gets to on the other side. And that's exactly what we're encountering here. The potential, that we start with is the potential that we end with. So what that means is we're going to go from the 7 centimeter mark to the 3 centimeter mark, because those are the points of equal potential. So it'll travel from the 7 centimeter mark to the 3 centimeter mark, which is 1 centimeter to the left of the hole, because it will travel to a region of equal potential. Right, and the potential was 3 volts. Let's take a look at this example. Each unit on the grid to the right represents 1 meter. 2 5 millicoulomb charges are placed on a y-axis as shown. A 40 kilogram charge of 1 millicoulomb is placed on the x-axis as shown. Find the net force on the 1 millicoulomb charge. Okay, this is positive. Since we weren't told that these are negative, we're going to see these as positive as well. So I'm going to call this, let me see, I'm going to call this one charge 1. I'm going to call this one charge 2, and thus this one will be charge 3. So what is charge 1 doing to charge 3? Since they're both positive, it's going to repel charge 3, right, in that direction. What is 2 going to do to 3? Well, same thing. Since it's the same magnitude of charge pushing on charge 3, it's going to be the same force but applied at an opposite angle. And if we use our parallelogram method of addition, I'm going to complete the parallelogram. And this would represent our net force. Okay, now how do we get our net force? Well, the first thing we're going to need to do is we're going to need to find the magnitude of the force of 1 on 3 and then the force of 2 on 3. And then once we have those forces, we're going to be adding up the x and y components of these, and that will help us. So first let's find the force of 1 on 3. That would be KQ1, Q3 over R squared. So that's going to be 9 times 10 to the 9 times 5 times 10 to the negative 3 times charge 3, which is 1 times 10 to the negative 3. And the distance between those, you can see this is a 3, 4, 5 triangle. So that's 4 units, that's 3 units, that must be 5 units. Makes it very easy to do the math on this. So 9 times 10 to the 9 times 5 times 10 to the negative 3 times 1 times 10 to the negative 3 divided by 25, and we get around 1,800 newtons of force. Well, since charge 2 is the same magnitude of charge pushing on charge 3, it's also going to have the same force. The force of 2 on 3 is also 1,800 newtons. So this is also the force of 2 on 3. Okay, but from a different direction. Now, to find the net force, we're first going to find the total force in the x direction. Now, to do that, we're going to basically be going F13 times the cosine of the first angle. Okay, and let's actually look at the picture down here so we can see it. Let me zoom in on the picture. If we were to kind of focus on this right here, the angle we're talking about there is a 53-degree angle. Now, when we start talking about those two for F23, we really should take the angle from 0 degrees. And that angle would be 180 minus 53, or 127 degrees. So keep those angles in mind as we find the following vector components. So the total force in the x direction would be F13 cosine theta plus F23 cosine theta. So it's going to be 1,800 cosine 53 plus 1,800 cosine 127. And what you end up getting when you add up all this is you get 0. Now think about why that makes sense. If you looked at the forces that are acting on this thing, and I'm focusing on those two vectors right there, okay? I'm going to color code these a little bit differently. So in gray, you can see I've got the forces in the x direction, and they're going equal and opposite. They are canceling each other out. So how do you get this net force right here? Well, it's really this force here plus that force there is going to equal that big long force right there. So when we add them up in the y direction, that's how we're going to get it. So the net force in the y direction, well, it's the same idea. It's F13, but now sine of theta plus F23 sine of theta. That's going to be 1800 sine 53 plus 1800 sine 127. Do that correctly, and that'll give you about 2,875 newtons directed upward. When the 1 millicoulomb charge is released from rest, how fast does it move when it's very far away? Well, there's a couple ways we could do this. We could find the potential energy of the system, and then the potential energy equals the kinetic energy when it's very far away. We could do it that way. And we already learned how to find the potential energy of the system. We would find the potential energy between 1 and 3 and between 2 and 3, right? Or another way we could do this is we could find the potential at 1, the potential at 2, so the potential at 1 would be K times Q1 over R1. That would be 9 times 10 to the 9 times 5 times 10 to the negative 3 coulombs divided by 5, because 5 meters is the distance between charge 1 and the 1 millicoulomb charge 3. And we would get 9 million volts of potential this way. And, well, number 2 is the same thing because it's the same charge. Charge 2 is the same charge. So also 9 million volts. Okay, what that means is V total would be 18 million volts. And the electric potential energy is Q times V, or 1 times 10 to the negative 3 times the 18 million. So one of the ways we can do this is if this is our potential energy and our kinetic energy is 1/2 mv squared, again, set them equal to each other. So Q times V equals 1/2 mv squared. That means V is equal to the square root of 2 times Q times the voltage divided by the mass. When we plug into that, we're going to go 2 times the charge is 1 times 10 to the negative 3 coulombs times the 18 million volts, all divided by, what was the mass? 40 kilograms. Go ahead and throw that in your calculator. and V comes out to about 30 meters per second. Once the 1 millicoulomb charge is gone, there is a single point P where the electric field is 0. Where is point P? Well, it would be right there. It would be right smack dab in the middle. Let's think about why that is. If this is a positive charge and this is a positive charge, they are going to be repelling each other in the middle. Because remember, electric fields point outward from positive charges, right? There's no electric field in the middle between the two. So that point would be the origin 0, 0. What is the electric potential at that point? Well, the electric potential at that point is going to be positive. The way we can kind of reason that out is because the electric potential energy at that point would be positive. But let's say we just looked at, let's say the voltage V1 equals K Q1 over R, and V2 is K Q2 over R. Well, since both charge 1 and charge 2 are positive, the voltages would be positive. The potential would just be V1 plus V2, both of them being positive. That means the total potential at that point would be also positive. It would be 2KQ over R, but positive. Sketch the graph. What is that going to look like between the points? So if this is voltage versus X, would look something like that. Again, I'm sketching it. I don't need to, you're drawing it to an arbitrary height. I mean, I could have drawn it this high, I suppose, but you just want to make sure that you have some sort of peak. The peak at the origin represents the positive electric potential. Describe how one of the 5 millicoulomb charges would be changed in order to make the potential 0 at point P. Okay, so to make the potential 0, let's think this through. For the potential to be 0, it means the potential energy would have to be 0, okay, at this point P. In order for the potential energy to be 0, you would essentially have to have a strong electric field. That's going to be the point. The place where the potential energy is 0 is going to be the place where you have maximum kinetic energy. Now, when you have an electric field in between those charges, so if this, let's say, is positive and this now becomes negative, now we establish an electric field going between those two charges, and you have a field strength right in the middle, right? So what we want to do is we basically want to change one sign from positive to negative. Now, after this modification, is the electric field 0 at point P? No. But the potential is. The potential 0, so you want to have the potential at this part right here. And what it's going to look like now is it's going to look like the electric field is again the negative change in displacement, change in potential over the displacement, meaning negative slope. There's your negative slope right there. Section 15.5, conductors in an electric field. What is the electric field strength inside a conductor? Use the diagram to explain the mechanism that causes this. The free electrons in a conductor make their way to the surface right next to the positive region. So if we look at the picture here, we can see the electric field established. It's pointing downward. That means this whole region is positive outside the conductor, and that whole region is negative outside the conductor. Well, this positive region is drawing the electrons in the conductor to that surface, meaning all those charges pile up, all those electrons pile up there. What that means is it leaves the other end of the conductor relatively positive. And in such, what have we done? We have set up an electric field of equal magnitude inside the conductor going exactly the opposite way. What this does is this creates a canceling effect, and thus the electric field inside of a conductor is zero. What are the boundary effects for an electric field at a conductor? Well, the boundary effects are such that the electric field is perpendicular to the surface or normal to the surface. What is true about the electric potential within a conductor? What mechanism causes this? Well, conductors are themselves electric potentials. They're equipotentials. Okay, so since the charges are free to move around the conductor, no work is done, which means there's no change in energy, and therefore there is no difference in potential. If there's no difference in potential, the potential is constant or equipotential. Let's take a look at this next example. A conducting sphere of radius 10 centimeters holds a 150 microcoulombs of charge, positive. Another sphere of radius 5 centimeters, so it's half as wide, is electrically neutral and is near the 10 centimeter sphere. Is there an electric force on the neutral conductor? Explain. Well, the answer to that quickly is a yes. Yes, there is. And here's basically why. A neutral conductor doesn't mean it has no charge, it means it has balanced charge. This has an excess positive charge, which means electrons were most likely taken off of this. So if we were to draw this, it would be like, for instance, you can see I have an unevenness of positive and negative charges, making this more relatively positive. Whereas over on this side, it would have a complete balance of positive and negative charges. Now, what happens is if this whole thing is positively charged, what it's going to do is it's going to pull all of the electrons all the way over to pile up on the left-hand side of the sphere, making the right-hand side relatively positive. This is called polarization. So yes, the charges in the neutral sphere will be polarized. This means the freely moving electrons in the conductor will move to the left side of that right-hand sphere. The result is an electrostatic attractive force. Positive attracts the negative. Now suppose the conductors are moved far apart. Well, if they're moved far apart, it lessens the force, and the charges right here would reestablish themselves back to neutral. But it's moved far apart, and then it's connected by a conducting wire. What are the charges on the sphere now? Well, the charges are going to flow until you have basically a net charge on the same, the net charge is the same on both, which means if you separate them really far, then this goes back to being 0, this goes back to 150 microcoulombs, and it's as simple as, well, the average of these. So 150 microcoulombs plus 0 divided by 2 means that each sphere is going to have 75 microcoulombs of charge when it all evens out. Does the potential energy of the system increase, decrease, or remain the same when the wire is connected? Well, the potential energy increases, okay? And the way you can see that is before, remember, potential energy is K Q1 Q2 over R. So before, we had U was equal to K times positive Q times negative Q over R, which means the potential energy was negative. And now the potential energy is equal to K times positive Q, positive 75, times positive 75. So they're both positive, divided by R, which means if you went from a negative, both being negatives, to a positive, your potential energy is now going to be positive. If your potential energy goes from negative to positive, your potential energy is increasing. Section 15.6, dielectric materials in an electric field. So if we consider an atom or a molecule of a non-conducting substance, the atom typically has a positive charge concentrated in the nucleus, as seen in this picture here. And the negative charge cloud is centered on the nucleus, so this whole thing is the charge cloud. However, if an electric field is applied to an atom, then the nucleus of the electron moves so that they are non-concentric, means the nucleus is shifted over just a little bit towards the right-hand side. And what that does is that creates a potential difference, because if this side is more relatively positive, this side is more relatively negative, and it sets up a small electric field within the atom. The atoms themselves become polarized, okay? And this is creating, right? This is creating an object called a dielectric. A dielectric is essentially an insulating material whose atoms become polarized when in the presence of an electric field. We quantify this effect of the electric field by defining what is called the dielectric constant, kappa. This is not K. This little letter K is called kappa, and is also known as the relative permittivity. The dielectric constant is intrinsic to the materials in question. So for instance, the kappa for silicon dioxide, which is basic sand, is a value of 3.9. The dielectric multiplies into this other constant called E naught, epsilon naught, not E naught. In all formulas, giving us a new value called the permittivity of free space. Section 15.7, capacitors. When positive and negative charges are separated from each other, electric potential develops between them. This is because the potential difference depends on how much charge is separated, how charge is stored and arranged in space. So what a capacitor does is a capacitor is a device that stores charge, and it stores it by holding positive charges on one side and negative charges to the other. Capacitor will always have equal amounts of positive and negative charges. And it is always said that thus it has a net charge of 0. However, the amount of charge on one side is Q, the other side is negative Q, and this creates a potential difference between the two sides of the capacitor. The basic equation for capacitance is the capacitance is related to the charge stored divided by the potential difference. The unit capacitor is the farad, denoted with a capital letter F. Most times it's going to be on the order of microfarads or nanofarads, much, much smaller units, but the farad is the basic unit. Capacitance only depends on the charge stored, the potential difference, and the distance between these plates. Well, capacitors, they store energy, and when the charges are stored, there are 3 different equations that will help for the storing of these capacitors. One is the potential energy. The electric potential energy would be 1/2 times Q times V, or 1/2 times the capacitance times V squared, or Q, the charge squared, divided by 2 times the capacitance. We have 3 ways to deal with electric potential energy stored by capacitor. So let's consider 2 plates of area A as separated by distance D. The plates carry equal charge Q with an opposite sign. Ignore edge effects. Okay, so this is basically what a capacitor does. A capacitor is normally hooked up to a battery. So this side would be hooked up to the positive side of the battery. This side would be hooked up to the negative side of the battery. Okay, and when the voltage is applied across the battery, what that does is the positive end of the battery pulls electrons from this plate all the way through the circuit, okay, leaving this whole side of the plate relatively positive. And what does it do? It repels and pushes those electrons onto this side of the plate, leaving this one more electrically negative. So that's essentially what a capacitor does, is it pulls electrons from one plate, deposits them on the other, as long as it's hooked up to the battery. Now, what you can always do is you can always disconnect a capacitor from the battery, and it will keep the same amount of charge stored. Let's take a look at how capacitors work from a mathematical point of view. The equation for capacitance, C, is equal to epsilon naught times the area divided by the distance between the plate. What this means is if the area gets bigger, you have the capacity to store more charge. If the distance between the plates gets wider, well, that means the electrostatic force that's pulling and pushing electrons off one plate and depositing on the other, well, that goes down. So spreading out the plates, lower capacitance. Bring the plates closer together, right? Then you're making that electric force of pulling negative charges off one plate, depositing on the other, a lot greater. Therefore, the capacity to store charge is greater and the overall capacitance is greater. So that's how this equation works right here. Epsilon naught is the what's called the vacuum permittivity, and it's a value of, I want to say 8.85 times 10 to the negative 12, if I remember right. But again, it's a number you don't have to memorize. It's given on the table of information on the AP exam. So now, using other basic equations, determine the electric field strength between the plates in terms of Q and A. All right, so let's first start with this idea here. Charge is equal to capacitance times voltage. Okay, and I'm going to solve that for voltage. Voltage is charge over capacitance. Now we know that capacitance is equal to epsilon naught A over D. We also know that the electric field is the voltage divided by the distance, the magnitude of it. The actual equation has a negative change in electric potential, but the magnitude of the field is just simply the voltage divided by the distance between the plates. Now, we can do a little substitution here. The first thing we can do if I can substitute for into this equation here, I can substitute for capacitance, this part here, and I can plug this right in there. And I get at the voltage is equal to Q over epsilon naught area over distance. Which when I figure this out, it's charge divided by 1 times distance over epsilon naught times area, or Q times distance over epsilon naught times area. So that's the voltage. That's a new value for voltage. Now if I take that and I substitute that for voltage here in place of voltage, I have a new value for the electric field. Okay, and it is the charge times the distance over epsilon naught times the area divided by the distance. Now that's d over 1. Okay, that's going to be the same as the charge times the distance over epsilon naught times the area times, we're going to multiply by the reciprocal of that, so that'd be 1 over d, and you can see the distance part cancels. And we end up with the charge over epsilon naught times A. And so what this tells you is the electric field is related to the charge stored and the area of the plate, how big the plate is. The bigger the plate, the weaker the field. Why the weaker the field? The bigger the plate, the field gets spread out because the electrons are spread out, and the electrons and protons and the atoms are spread out. So if the plate's bigger, the electric field gets spread out, it's less dense, which means it's not as strong. If the area is much smaller plate, the electric field lines are now more dense, they're more closely packed, which means they're stronger force that would be applied on any charge put in there, stronger field strength. Let's take a look at the next example. You are asked to build a capacitor out of 2 sheets of metal. If the sheets are to be 1 millimeter apart and the plates are to be a square, how long is one side of the capacitor supposed to be? Well, first let's figure out, let's take the equation that we were working with. So capacitance is equal to epsilon naught times the area over the distance. And how about this? Let's go ahead, this is kind of the plan. Let's solve for the area. And then remember, area of a square is just the side squared. It's one side times the other side. That's the area of a square. So we can find the side by taking the square root of the area once we get there. So to find the area, we're going to multiply the capacitance times the distance, divide that by epsilon naught. So the capacitance is 1 farad. The distance is 1 times 10 to the negative 3 meters, or you could write it and just move the decimal 0.001. Could do that. And that's divided by the epsilon naught is the permittivity of free space, and that constant is available on the table of information, and it's approximately 8.85 times 10 to the negative 12. When we put that in our calculator, we will get about 1.13 times 10 to the 8 square meters. Now, we already established that area is equal to side squared, so the side is the square root of the area, or the square root of 1.13 times 10 to the negative 8 square meters, and that's approximately 10,630 meters long. So in other words, the side of this piece of metal would have to be over 10 kilometers long in order to store 1 farad. That tells you how big, how much 1 farad of capacitance really is. You have to have a pretty big capacitor to store 1 farad. Let's consider a capacitor connected to a voltage of V. The charge on the capacitor is Q. What will be the new capacitance C prime, the new potential difference V prime, and the new charge Q prime if the plate separation is doubled? So a couple of things you should be aware of. Well, the capacitance is equal to epsilon naught A over D. And here's basically what we're told. Epsilon naught, that's a constant, so I'm just going to replace that with a 1. We're not told that the area of the plate changes, so I'm going to leave that as a 1, but we're told that the plate separation D has doubled, which means the capacitance is 1/2 as much as it used to be. Now, since Q is equal to capacitance times voltage, the capacitance is 1/2 as much. The voltage, let's see, what will be the voltage? Well, the voltage is going to stay the same. The voltage is going to stay the same because the plate separation doubled. The voltage across the capacitor depends on the voltage across the battery, because remember, the battery is pulling electrons from the positive and depositing on the negative, right? So whatever the voltage on the battery is the voltage across the capacitor. It's always going to be the same. So since the voltage on the battery didn't change, that's going to be a 1. That means the capacitor, the charge stored is 1/2 as much. So we have the same voltage, 1/2 the capacitance. That means 1/2 the charge stored. Okay, and the potential energy is proportional to CV squared. So the capacitance is 1/2, but the voltage is the same. You can see that the energy stored would be 1/2 as well. Okay, and we can kind of write this out in words. Voltage depends on the potential difference from the battery, which is the same, so voltage is the same. If the area stays the same and the distance doubles, the capacitance will cut in half. If the capacitance cuts in half and the voltage stays the same, the charge will cut in half. And if the capacitance cuts in half and the voltage stays the same, then the potential energy will cut in half. Consider capacitor C charged to voltage V and disconnected from a charging source. So now we take the battery out of the equation. Now what's going to happen once we take the disconnect the capacitor from the battery is the charge will remain constant unless the capacitor is discharged, right? And the charge goes elsewhere along the conducting wires, like let's say through a light bulb or some sort of resistor, okay? Some sort of electric current flow. But if it's not, if it's just on a capacitor and it's stored there, then the charge will remain the same. So I'm going to start there. Now, one thing that we should be able to consider is that the potential difference is equal to the electric field times the distance. The electric field is based upon, remember we talked about this earlier, the charge stored and the area, both of which are not changing. Since the area is not changing, the plates are not getting bigger or smaller, the charge isn't changing, the electric field will not change either. So I'm going to put a 1 for that. But the distance doubled. That means the voltage between them will double as well. Another way we can show the charge is staying constant is charge is equal to C times V. If the, I guess we'll hold off on that. Let's focus on capacitance. So capacitance is equal to epsilon naught area over distance. Well, the area stayed the same. Epsilon naught is a constant, so I'm just going to put a 1 for that. But the area stays the same, so I'm going to put a 1 for that. The distance is doubled, so I'm going to put a 2 for that. The capacitance is half as much. And if we look at charge being capacitance times voltage, take a look. The capacitance is half. The voltage is doubled. Well, a half times a double is 1. The charge didn't change. So again, the E field is constant and the distance doubles, the voltage doubles. Remember, the E field is constant because the charge, the plate area is constant, and the distance, the charge that's on the plate is constant and the area is constant. So the charge is constant because the disconnected from the battery, and it's going to have the same amount of charge stored, no more, no less, as long as it's not discharged in any way. And if the area of the plate stays the same and the distance doubles, the capacitance will cut in half. Okay, so the following diagram shows how a dielectric actually works. First, we start with uncharged parallel plates with no dielectric. Again, the dielectric is the insulating material. Could be air, it could be a piece of paper, it could be some sort of plastic. It's some insulating material that you place in between the charged plates. The capacitor is now charged with an electric field between the plates, right? And there's a vacuum between the plates. Now all of a sudden we put the dielectric between the plates, and the atoms are going to interact with the electric field, with the exterior electric field. And remember what we drew in the picture. I'll go ahead and remind you of that. Remember, the nucleus of each atom is able to shift over within the electron cloud of each atom, creating a potential difference within the atom and thus an electric field within the atom. And that happens true with each of these. So what we establish is an electric field. So we have a larger electric field, a larger external electric field applied across the dielectric in between the capacitor plates. The dielectric itself, right, because the atoms are being polarized, we're now producing a weaker electric field inside. Okay, now what this does is it weakens the strength of the exterior electric field between the plates. So dielectrics are one way to decrease the electric field between capacitor plates.